In this lesson, we will discuss the a priori algorithm for finding frequent patterns efficiently. We will start with discussing the downward closure property of frequent patterns, which makes the core idea on how the a priori algorithms prunes infrequent patterns. The downward closure property of frequent items states that any subset of a frequent item set must also be frequent. Here's an example. If we already know that beer, diaper, and nuts is a frequent item set, then any subset like beer diapers, beer nuts, beer, nuts, and so on, all of these item sets are going to be frequent. So now the question is how to use this property to eliminate patterns that are infrequent. If you think about it, if we just flip the script and we say if any subset of an item set S is infrequent, then there is no chance for S to be frequent. So if the subset is infrequent, then also the bigger set that contains the subset is going to be infrequent. This idea is formalized in the a priori pruning principle, which states that if any subset of an item set S is infrequent, then S itself cannot be frequent. Let's walk through an example to understand how the a priori algorithm works. Suppose that we have a database with 4 transactions and we set up the minimum support to 2. The algorithm starts with scanning the database to get the candidate item set of size 1, which consists of 5 item sets A, B, C, D, E with their support. Notice that the candidate item set is not verified yet. After that, the algorithm prunes the item sets that do not satisfy the minimum support. In this case, the algorithm got rid of D with support 1. Next, the algorithm generates candidate item sets of size 2 based on the content of the frequent item sets of size 1. Notice that the algorithm should be carefully implemented so it won't do unnecessarily work while it generates these item sets. One strategy is sorting the item sets alphabetically, so we make sure that the generation process is very systematic. As you can see, we have AB, then AC, then AE, then it goes to B and C and so on. After that, the algorithm performs a database scan to obtain the support information from the database so it can identify those item sets that need to be pruned. Notice that the database scan itself is a very expensive operation, so we only need to do it when it's necessary, and when we have to do it, we try to check the fewest number of item sets. At this point, the algorithm pruned the item sets that did not meet the minimum support and converged to the frequent item sets of size 2. To generate candidate item sets of size 3, now the algorithm has more opportunities to be more aggressive in the pruning process because the downward closure property can be directly applicable here. Let's say in a very informal way that when the algorithm generates the next candidate of size 3, it will consider the item sets that share a prefix like BCBE, and it will not consider item sets that share a suffix like ACBC. We will explain this in a minute. Now that we got the next candidate, we go and check this candidate against the database. At the end, the algorithm was able to find frequent item sets of size 1, size 2, and size 3. Let's go back to the question, why is it incorrect to generate ABC from AC and BC? They shared a suffix but not a prefix. If you pay attention to candidate item sets of size 2, you are going to see that AB has support 1, which doesn't meet the minimum support. AB is a subset of ABC, which means given the downward closure property, if a subset of a bigger set S is infrequent, that means the bigger set is infrequent. That's why we don't need to even look at anything that does not share a prefix. Here's the outline of the a priori algorithm. First, the algorithm scans the database to get frequent one-item sets. Then it goes on a loop to generate k+1 candidates from k frequent items, then test the frequent items against the database and continue to do that until no frequent or candidate set can be generated. At the end, all those frequent sets are unioned together and returned. This is the pseudocode of the algorithm, the candidates and the frequent item sets, the initialization, and getting the first frequent one item set, going through the loop to get the candidates, then the frequent item sets. At the end, we union all of those frequent item sets that the algorithm was able to find. The performance of the a priori algorithm depends a lot on implementation tricks that allows the algorithm to prune item sets without accessing the database unnecessarily. In this example, we will show how the algorithm generated 2 candidates of size 4, but we were able to prune one of them. Let's walk through this example. The algorithm is in a place where it needs to generate candidate of size 4 based on the frequent items of size 3. Following the algorithm, those share the same prefix, so it generated ABCD, and those share the same prefix AC, and it generated ACDE. One trick that can be implemented at this point is checking all subsets of size 3 against the frequent item set of size 3 and make sure that at least so far all of these subsets satisfy the minimum support. If they satisfy the minimum support, this is viable and should be checked against the database. But for the case of ACDE, ADE is not part of the frequent item sets of size 3, which means this can be safely pruned. The pseudocode of candidate generation shows how inserting this condition has infrequent subset can help with identifying this case where we can disqualify the candidate based on the content of the frequent item set of k-1 size. In summary, we discussed the a priori algorithm for finding frequent patterns efficiently.